che mamari nina. Tura la ba. Kofana, lana, tula ba.
An international fleet of science probes is congregating on Mars. They are scouring for evidence of past life. Testing technologies are required for humans to visit this lonely world. The Red Planet has beckoned eras of dreamers and spaceflight pioneers to visualize crossing the vast gulf between planets. Long-standing questions swing in the balance. What is humanity's destiny in space? Could we construct a second home on Mars? Mission planners have long understood that it is impossible to land on Mars. The atmosphere is thick enough to melt space capsules, which hit it running at 15,000 kilometers an hour. It is so thin that even a wide aeroshell plus a giant parachute is needed. Percy, the Mars 2020 Perseverance rover, used an ingenious system of rockets. Furthermore, an innovative sky crane to get the job done. Landing a team of astronauts is a difficulty waiting to be cracked. Percy is among the most sophisticated mobile machines ever constructed. Its minor affiliate, Ingenuity, is the ultimate drone, testing controlled aviation for the first time in another world. From the impressive images Percy and other probes send, it is easy to believe Mars is like the deserts of Earth. For at least a century, forecasters have imagined that it should not be too challenging to explore in person if we could get there, to pioneer a frontier of liberation and wealth. Furthermore, as Elon Musk puts it, to make a backup copy of Earth's biosphere in case of disaster. The actual Red Planet is an illusionist with a long history of tricking us. Colder than Antarctica, bone dry, intense, harmful grit underfoot, and killer radiation from persistent rain above. A miserable world. The Mars we desire has never been the Mars that is. For millennia, the bright amber planet has been teasing human fantasy. As they orbit, Earth and Mars come nearest every 780 days, dubbed a planetary opposition. It is the best time to monitor the Red Planet, which over a few weeks seems to slow down, backtrack, then speed forward again. Perplexed by this impulsive retrograde motion, Egyptian observers saw Mars as a hawk-headed humanoid god flying back and forth between the living and dead kingdoms. Sumerian astrologers considered Mars a quick, whimsical incendiary god from its odd motion. On May 5th, 357 BCE, the Greek philosopher Aristotle followed the half-moon passing in front of the Red Planet and recognized that Mars must be farther away than the Moon. He would have been astonished by how much Mars is 200 times more distant. Chemical rockets that take 3 days to get to the Moon would take 7 months to reach Mars. Future nuclear thermal rockets might cut that journey to less than 3 months. That is still a long time to spend contained in a small spacecraft. The minor planet may have been hit by something even more noteworthy. As you fly from south to north, Mars' terrain sinks, from red and orange highlands down to green and blue valleys. Mars's whole northern hemisphere is a giant concave ellipse draping over 40% of the planet. If this is a crash site, the incoming object would have been about the dimension of the dwarf planet Pluto. It would have transformed Mars, shutting off its internal dynamo, obliterating its protective magnetic field and destroying the chances for a life-sustaining atmosphere. When Elon Musk's would-be settlers set sail for Mars, they must accept that they will never again take a breath outside their helmets or habitats. They will have spent months crossing the void in a desolate world with a lethal environment. In October 1610, Galileo Galilei recorded the first telescopic observation of Mars. 26 years later, Francesco Fontana made the first known illustration of the planet, saying it looked like a black pill. The Dutch brothers Christian and Constantine Huygens had evolved much better optics by 1650. Christian sketched an irregular mark on Mars, living in the wetlands of Holland. He thought it looked like an enormous marsh, so it became known as the Grand Marsh Theaetas Major. Constantine found that the rotating feature finds the day length on Mars like Earth. 7 years later, Giovanni Domenico Cassini refined that figure to 24 hours plus 40 minutes, very close to what astrophysicists measure today. Cassini also logged the first observation of Mars's south polar cap. Watching the changing faces of Mars, Cassini imagined it must be pretty like Earth. 3 billion years ago, Mars may indeed have been Earth-like. Volcanoes build the atmosphere, steam and mist and flowing water, filling early seas with more fluid than the Arctic Ocean on Earth. In 1997, Sojourner, NASA's first Mars rover, found the outflow of a cataclysmic flood. Beginning in 2000 for the Mars exploration rovers, Spirit and Opportunity found stacked strata of rock laid down by flowing water over thousands of years. Furthermore, little rounded, iron-rich concretions nicknamed blueberries must have formed in silt pockets lying under salty water. But what of water on modern Mars? NASA's Phoenix found evidence in 2008 soft landing at high northern latitude. Its rocket plumes blew away surface dust, exposing some white material. Digging a shallow trench, the tiny probe revealed more, which disappeared within a day. Furthermore, liquid drops appeared on the lander's legs, then changed. In August 2012, the Mars Science Lab, Curiosity, rolled. Trekking through dry stream beds between the banks of ancient watercourses, and across the alluvial fan at the mouth of a long-dead river. Perseverance joined Curiosity in 2021, landing in a once-flooded crater, finding the clay-rich rocks of an ancient river delta. These hardy robot geologists found layered terrains, and each is built by episodes of flowing mud with dry times in between. These wet periods ended long ago. Today's Mars seems a lifeless desert, and a lonely landscape cries out for company. In 1699, Christian Huygens did not think Mars was so desolate. His last book, Cosmos Thoros, imagined that the worlds of the solar system must harbour plants and animals, though they would differ from those on Earth. Huygens saw no reason that life on the planets should not be intelligent. They led comparable lives. Furthermore, he also pointed out how important water would be to those creatures. The Moon is rich in aluminium, titanium, silicon, and magnesium. Asteroids add carbon, cobalt, platinum, molybdenum, and nickel. Mars has abundant iron and other metals, especially near its enormous volcanoes. Mars' key ingredient is water ice, split to make breathable oxygen and hydrogen fuel. Percy is testing this hypothesis, breathing in carbon dioxide and electrochemically breaking out the oxygen. The water beneath the surface, plus carbon dioxide from its atmosphere, can be rearranged to make methane and oxygen. Use that oxygen to burn the methane, and you can launch rockets. By making propellant on Mars, the cost of getting back to Earth drops by at least a factor of 5. To conjure up a space-based civilization, we can bring with us only tools and talent, small factories and power generators. We must hunt and gather the rest. In 1704, Giacomo Filippo Morandi guessed that dark rings around Mars' poles might be melt lines. Could the poles be ice caps? He wondered. 9 years later, Wilhelm Herschel declared yes. Mars' poles are water ice, and he thought that the broad, dark equatorial patches must be oceans. Herschel daydreamed about what it might be like to sail those waters. Mars lost its oceans before life emerged out of the seas on Earth. The northern desert lowlands, the flattest topography on any known planet, look like an ancient sea floor. The polar ocean may have covered a third of the planet, up to 4 kilometers from Mars. In 1786, Herschel speculated that Martians enjoyed a similar situation. He realized the Martian atmosphere must be fragile. The planet is enveloped in sparse carbon dioxide, and there is very little water in the air. There is methane, which could come from hot underground geology. The methane level sometimes blooms and then disappears. Furthermore, many experts wonder, might something be living below the surface? Bizarrely, Johann Schrader proposed Mars had no solid surface, just drifting clouds and misty rain in 1789. Schrader's shifting scene was just because of the unstable air of Earth above his giant telescope. The true story of Mars's atmosphere is becoming more apparent. Going back at least 1 billion years, intense ultraviolet radiation from the Sun and the sputtering solar wind bombarded the minor planet with its low gravity and frail global magnetic field. Mars could not hold on to its protective gas envelope, and most of its air was lost to space, and the rest of its water was absorbed into the ground. Back in 1831, none of this dreadful history was known. Johann Heinrich Modeler and Wilhelm Bader crafted accurate Mars maps. They placed their zero longitude line through a feature that will later be named Sinus Meridian Bay. The Opportunity rover explored it for 13 years, sending home the stark, withered landscape images. It is easy to imagine standing on Mars yourself, gazing at the weathered rocks. Everywhere our probes look, they see evidence of past liquid water. Though there are no oceans today, there is plenty of hidden ice. The Mars Reconnaissance Orbiter MRO recorded eroded cliff faces, exposing compacted frozen water over 100 meters thick in some places. MRO's radar revealed up to 2 kilometers of ice on passes over the poles. It has been laid down in layers, suggesting that Mars's climate may cycle between warm and relaxed times. Zooming in from orbit, we can see dark streaks that appear and disappear on the slopes of steeper craters. They look a lot like desert rain gullies on Earth. Furthermore, many researchers thought they might blow salty water. New analysis suggests that the larger ones, at least, are dry. Streams of rounded sand grains tumbling over one another and flowing like the liquid in the low gravity of Mars. The small ones seemed wet. In 1863, astronomer Camille Flannery picked up the idea of intelligent aliens, publishing the first of his 8 books about life on the planets. The Plurality of Inhabited Worlds became an all-time bestseller. Charles Darwin's notion that species develop in response to their environment led Florian to speculate that various planets would cause creatures unlike Earth. Drilling into the rocks, Mars rovers have shown the building blocks of life to be plentiful. Clay minerals would have filtered salts and harsh compounds from the primeval flowing waters. Many types of microbes now living on Earth almost indeed could have survived on ancient Mars. No photos, fossils, or direct chemical evidence of life have turned up. Around 1864, the Vatican became concerned about the state of grace of the Martians. Father Pietro Angelo Seici of the Roman College Observatory charted where they might live. He renamed Huygens Syrtis a prominent feature, calling it the Atlantic Canal. Sacchi intended no reference to intelligent design, but his term canali would cause much confusion over the following years. At the same time in England, astronomer William Moss made Mars maps of his doors that were near-sighted, but his charts were more detailed than before. Sensing a great story, science writer Richard Anthony Proctor blasted the doors maps out to the public. The Suez Canal was completed in October 1870, making news worldwide. The Panama Canal was in the planning stages, and many people connected the Strait Canal on Mars maps and these fabulous works of engineering on Earth. There are many ancient water channels all over Mars, but there is no technology in their shapes. Nathaniel Green, an artist by day and astronomer by night, painted the most accurate Mars chart. In America, the self-taught astronomer Asaph Hall noticed something no one else had: 2 tiny moons, Phobos and Deimos. Maybe bits of Mars flung into orbit by giant effects long ago. Or they may be asteroids captured by the planet's gravity, with Mars close within just 56 million kilometers of Earth. Giovanni Schiaparelli mapped it, though he, like Dies, was nearsighted and colorblind. Schiaparelli could somehow extract more from the telescope than others. He too called the lines he saw on Mars canali, giving them whimsical names from classical literature still used today. Some Mars oppositions are closer than others. While Earth's orbit around the Sun is circular, Mars' orbit is much more elliptical. During Mars' southern autumn and winter, the hemisphere is tipped away from the Sun, and the entire planet is farther away, making those seasons longer and colder, with a subsequent close opposition in 1879. Some Pirelli came to believe he was seeing pairs of straight canali. Harvard College observatories, William Henry Pickering, declared Martian canals were only visible because plants grew along their banks. All speculation about large engineering projects by smart Martians were put to rest on the night of July 14, 1965, as NASA's Mariner 4 flew by Mars in the probe's 21 images. Mars looked much more like the Moon than the Earth. Worse, Mariner could not find a protective magnetic field. Harsh solar wind and cosmic radiation would have scoured the planet for millennia. It is tough to imagine how even primitive life could survive here. In 1892, Camille Marion was still filling his imaginary Martian canals with water. He speculated they were the reflection of old rivers by the inhabitants for general water distribution, that the actual habitation of Mars, by being superior to our own, is very probable. Pouring more into flamboyance, illusory waterworks, Pickering asserted he had observed up to 40 lakes. At about the same time, a wealthy, world-travelling American diplomat felt he needed a career change and a personal passion project. Percival Lowell had read full Marion's books, and he made plans to look for Martians during the coming opposition of 1894. Pickering helped Lowell rig 2 telescopes on a hilltop in Flagstaff, Arizona. The new Lowell Observatory stared at Mars all summer long, but Lowell, an untrained observer, saw only what he believed. He sketched a planet comprehensive irrigation system, transporting billions of gallons of melted polar snow to tropical oases, the irrigated agricultural projects of an advanced race. During the same opposition, astronomer Edward Barnard, wielding the California Lick Observatory's more giant refracting telescope, could not find a single straight line anywhere on Mars. Furthermore, when William Campbell examined Mars with a spectroscope, he saw not a trace of water. English astronomer Edward Maunder showed how straight lines on Mars could be optical illusions. Undeterred, Percival Lowell sprinted across America on a lecture tour in 1895, promoting his book, Simply Mars. A story-thirsty public bought his tales of Martian waterworks by the thousands. The real Mars is a parched planet, and though tilted rocks tell us, there were lakes here long ago. The Spirit rover caught one in the act. 486 Martian days after landing, today dust devils swirl across the barren terrain. Curtains of desiccated grit sweep up the hazy sky from rugged canyon cliffs. Dry, sandy landslides garnish steep crater walls and clump on the floors. In 1896, Percival Lowell began observing with an even bigger refractor, but could not see his glaring error. Lowell carried on for 20 more years, imagining over 450 canals, with vegetation seduced by the drama of a desperate civilization. They were combating climate difficulties as their dying world dried to a planetary desert. Mars's climate did change. It happened long before Lowell's time. Mars wobbles tens of degrees over hundreds of thousands of years, much more wildly than Earth. Without a large moon to stabilize it, when Mars points a pull toward the Sun, billions of tons of CO2 might be released, unleashing the ethics of greenhouse warming. This might melt subsurface ice, letting the water flow. The temper can never last. In his 1899 novel, The War of the Worlds, H.G. Wells found drama on the doomed planet. An advanced race of Martians comes to conquer Earth. Furthermore, enslave humans as work animals. Earth sent 2 Viking landers not to subjugate but investigate in 1976. They found very active, intriguing surface chemistry, but no life. In 1985, the idea of a living Mars captured Lowell Observatory Carl Lapland. He claimed to have photographed 38 canals. It is vital to remember that most of these observers were good astrophysicists wielding the best telescopes of their day. They saw what was not there as a lesson, perhaps for those who dream of settling Mars today. In 1909, at the Maiden Observatory near Paris, astronomer Eugene Antonio could find no linear canals, yet the idea of an alien civilization had seduced the public. American novelist Edgar Rice Burroughs released the first of his 11-volume tale depicting heroic John Carter on a fictional Mars. Today's Mars rovers are finding a desert world too. Curiosity trekked around a wide field of dark dunes. Rolling like waves on an ocean, the sandy mounds migrate across the terrain. The orbiting high-rise camera caught Curiosity at work in what has been known as the Bagnoli Dune Sea. In 1921, Mount Wilson Observatory astrophysicists measured surface temperatures on Mars, finding them to swing from 15 Celsius at midday to a lethal minus 85 Celsius just before sunrise. Astronomer Walter Sidney Adams found only tiny quantities of oxygen and water at the Yerkes Observatory. Gerard Kuiper showed the Martian air to be all unbreathable carbon dioxide. Mars continued to entice explorers in 1949. Rocket pioneer Wernher von Braun wrote Project Mars. It was a sci-fi novel full of tactical engineering and a familiar plot. A multinational crew from Earth visits intelligent humanoid Martians trying to save their world. A year later, Ray Bradbury's Martian Chronicles placed a human colony on Mars to escape a nuclear war that devastated Earth. In 1952, von Braun published an enhanced Mars project, adding a comprehensive technical workup for an extensive scale space program. After 1,000 launches of people, propellants, and parts, a flotilla of 10 spaceships and 70 crew members would journey across the Gulf between planets to spend 444 days on Mars. Was the Mars project a rough draft for what would become NASA's Mercury, Gemini, and Apollo projects? In 1955, Paramount Pictures released Conquest of Space, modelled on von Braun's adventurous plans. To reach the Red Planet, engineers realized it might take more power than chemical rockets can produce in the US. Los Alamos National Lab Project rover began an effort to harness atomic vision to drive spaceships. The astronaut's crew capsule would be placed many meters from the radioactive engines. Getting to Mars faster would cut astronauts' dose of solar and cosmic radiation. Project Orion, a different approach to nuclear rockets, started in 1958. The idea of detonating nuclear bombs behind a ship to push it along. It was called pulsed plasma wave propulsion. Outrageous as it seems, this method could offer rapid transport to Mars and the rest of the solar system by 1961. The US nuclear rocket engine NERVA program had accumulated 17 hours of engine testing. In the Soviet Union, engineers were working on their nuclear thermal rockets. As late as 1962, the US Air Force made Mars maps with straight canal lines. Someday, a crewed expedition to Mars and return may become the mission assignment. To accomplish that assignment, Kraft Hierarchy, a visionary German-American engineer, introduced the idea of ganging together clusters of nuclear rockets. He thought his modular approach could bring Mars and Venus within reach as early as the 1970s. Furthermore, he identified the most efficient launch windows to reach these planets. Eric believed that human expansion throughout the solar system is a fundamental right. Furthermore, we are at our most dignified when we apply the laws of physics to elevate and protect our freedoms. In 1968, von Braun's visions would drive the Boeing company to propose the Integrated Crew Interplanetary Spacecraft concept. It bundled up to 5 nuclear thermal stages to propel astronauts and probes to the nearest planets. It would have cost half again as much as the Apollo moon program. It might have delivered the first crew to Mars by 1986. President Richard Nixon, fearing the political consequences of a catastrophic mission failure, would support only a space shuttle. Though subsequent US presidents would ask for various Mars programs, human space activities would remain confined to low Earth orbit for more than half a century. By 1990, some planners realized that bringing everything with you space programs were not workable. To remedy this, engineers Robert Zubrin and David A. Baker proposed the Mars Direct concept. Its motto, travel light. Furthermore, live off the land. By making rocket fuel from the planet itself, explorers could ensure themselves a ride home. By 1993, critical ideas from Mars Direct had found their way into NASA's Mars Design Reference Mission. Consistent congressional support for humans to Mars never materialized. In recent years, giant aerospace companies and small private startups have all adopted bits of Mars Direct. Boeing's affordable Mars mission would send a solar electric sailing ship from low orbit. Astronauts would descend, protected by an inflated aeroshell, touching down like the Apollo missions, to find a landed habitat waiting. They would return to orbit like last century's moonwalkers for the long trip home. In contrast, Lockheed Martin proposes a Mars orbiting base camp. It is built by stacking pairs of modules, 2 tank farms, 2 habitats, 2 rocket propulsion units, redundancy for safety, far from Earth. Astronauts make sorties to the surface with a single-stage lander. This surface-to-orbit shuttlecraft does not depend on fuel made on Mars. Younger, more aggressive companies are thinking bigger. Elon Musk's space exploration company is developing Starship, and it has transported massive payloads and many people across Earth and orbit. Furthermore, bringing millions of tons of material to the surfaces of planets, moons, and asteroids. Like von Braun and Eric before him, Musk is focused on solving transportation around the solar system. SpaceX's eventual goal is to make Earth life multi-planetary and build a civilization on Mars. In not-so-friendly competition with SpaceX, Blue Origin, led by Amazon founder Jeff Bezos, is developing large boosters of its own. Blue Origin's vision is to extend civilization into space to preserve Earth's climate and maintain it as a flourishing biosphere by moving its heavy industry and power generation. Furthermore, constructing city-sized accessible flying habitats from materials already in space on the Moon, asteroids, and comets. Video game makers, too, promoted the adventure of populating Mars and the rest of the solar system. Furthermore, some visionaries foresee the eventual terraforming of Mars and warming it up and making it as Earth-like as possible. These world builders must find enough greenhouse gases to heat the planet, then replenish its thick atmosphere. Furthermore, restore its water as the vapor escapes to space. Still, more challenges lurk on the trickster planet. Mars's surface is everywhere loaded with toxic, caustic perchlorates, up to 1% of the sands, putting astronauts at high risk for thyroid problems and cancer. Other invisible dangers cascade from the sky, unhindered by the thin atmosphere, the constant rain of cosmic rays from interstellar space. Furthermore, energetic particles from solar flares are pelting the planet. Despite the many intriguing renderings of doomed cities on Mars, settlers will have to spend most of their time in roofed shelters for many generations to come, or underground. There may be hope. The rise of autonomous machines, advanced robotics, artificial intelligence, and augmented reality can extend human senses to the surface of the red planet. Furthermore, someday we may send devices to terraform Mars on their human émigrés from Earth, building communities on a ready-made planet. Mars will come into a favourable position for launching human crews in 20 or 23. Mars has seduced many seeking notoriety, promising a new world to explore or exploit. Ingenious engineering may find elegant solutions for how to get us to Mars. What becomes of us once we get there? Do we visit the polar caps of Mars as we do on Earth? The northern polar cap and encircling dark dune field of Vastitas Borealis are visible at the globe's top. White water ice clouds envelop the most prominent volcano peaks, including Olympus Mons near the western limb, Alba Patera to its northeast, and the line of Tharsis volcanoes to the southeast. East of the Tharsis rise can be witnessed the enormous near-equatorial gash that marks the canyon system Valles Marineris. Sometimes called the Red Planet, Mars has long been associated with warfare and slaughter. It is named after the Roman god of war. As long as 3,000 years ago, Babylonian astrologers called the planet Nergal, for their god of death and pestilence. The planet's two moons, Phobos, Greek fear, and Deimos, terror, were named for two of the sons of Ares and Aphrodite. Mars has recently intrigued people for more significant reasons than its baleful appearance. The planet is the second closest to Earth after Venus, and it is usually easy to observe in the night sky because its rotation lies outside Earth. It is also the only planet whose solid surface and atmospheric phenomena can be seen in telescopes from Earth. Generations of assiduous studies by Earthbound observers, extended by spacecraft observations since the 1960s, have revealed that Mars is like Earth. Like Earth, Mars has clouds, winds, a roughly 24-hour day, seasonal weather systems, polar ice caps, volcanoes, canyons, and other familiar features. These are intriguing clues that Mars was even more Earth-like billions of years ago than today. With a denser, warmer environment and much more water, rivers, lakes, flood channels, and perhaps oceans. By all indications, Mars is now a sterile, frozen desert. However, close-up images of dark streaks on the slopes of some craters during Martian spring and summer suggest that at least small volumes of water may flow seasonally on the planet's surface. And radar reflections from a lake under the South Polar Cap suggest that water may still prevail as a liquid in protected areas below the surface. The presence of water on Mars is considered a critical issue because life, as it is presently understood, cannot exist without water. If microscopic life forms ever originated on Mars, there remains a chance, albeit a remote one, that they may yet survive in these sheltered, watery niches. In 1996, a team of scientists reported what they concluded to be evidence for ancient microbial life in a sample of meteorite that had come from Mars. But most scientists have disputed their interpretation. Since the end of the 19th century, Mars has been considered the most hospitable place in the solar system beyond Earth, both for indigenous life and human exploration and habitation. Speculation was rife that the so-called canals of Mars, complex systems of long, straight surface lines that remarkably few astrophysicists had claimed to see in telescopic observations, were the formations of intelligent beings. Seasonal changes in the planet's appearance, attributed to the spread and retreat of vegetation, added further to the professed evidence for biological activity. Although the canals were later determined to be illusory, and the seasonal adjustments geologic rather than biological, scientific and public interest in the possibility of Martian life and exploration of the planet has not faded. Mars has taken on a special place in popular culture during the past century. It has served as inspiration for generations of fiction writers, from H.G. Wells and Edgar Rice Burroughs in the heyday of the Martian canals, to Ray Bradbury in the 1950s and Kim Stanley Robinson in the 90s. Mars has also been a critical theme in radio, television, and film. Perhaps the most notorious case being Orson Welles' radio play production of H.G. Wells' novel War of the Worlds, which assured thousands of unwitting listeners on the evening of October 30, 1938, that beings from Mars were invading Earth. The planet's mystique and many genuine mysteries remain a stimulus to scientific inquiry and human imagination. Mars moves around the Sun at a mean distance of 228 million kilometers, 140 million miles, or about 1.5 times the distance of Earth from the Sun. Because of Mars' elongated orbit, the distance between Mars and the Sun varies from 206.6 million to 249.2 million kilometers, 128.4 million to 154.8 million miles. Mars orbits the Sun once in 687 Earth days, which means its year is twice as long as Earth's. At its closest approach, Mars is less than 56 million kilometers, 35 million miles from Earth, but it recedes to almost 400 million kilometers, 250 million miles, when the two planets are on opposite sides of the solar system. Mars is easiest to observe when it and the Sun are in opposite directions in the sky, i.e. in opposition, because it is then high and shows a lighted face. Successive oppositions occur about every 26 months. Oppositions can take place at different points in the Martian orbit. Those best for viewing appear when the planet is closest to the Sun and Earth, because Mars is the brightest and most prominent. Close oppositions occur every 15 years. Mars spins on its axis once every 24 hours 37 minutes, making a day on Mars only a little longer than Earth. Its axis of rotation is inclined to its orbital plane by about 25 degrees, and, as for Earth, the tilt gives rise to seasons on Mars. The Martian year comprises 668.6 Martian solar days, called sols. Because of the elliptical trajectory, southern summers are shorter, 154 Martian days, and warmer than those in the north, 178 Martian days. However, the situation is changing such that 25,000 years from now, and the northern summers will be the shorter and warmer ones. In addition, the tilt of the axis is changing on a 1 million year timescale. During the present epochs, the obliquity may change from close to zero, at which times Mars has no seasons, to as high as 45 degrees, when seasonal differences are extreme. Over 100 million year timescales, the obliquity may reach values as high as 80 degrees. The seasons of Mars, a result of the planet's inclination of 24.9 degrees to its orbital plane. At present, southern summer occurs when Mars's elongated orbit brings it nearest the Sun. As the seasons change, the polar caps grow and shrink. The southern cap extends about 5 degrees more towards the equator than the northern cap at its maximum size. Mars is a minor planet, more significant than only Mercury and more than half the size of Earth. It has an equatorial radius of 3,396 kilometers, 2,110 miles, and a mean polar radius of 3,379 kilometers, 2,100 miles. The mass of Mars is only 1/10 the terrestrial value, and its gravitational acceleration of 3.72 meters, 12.2 feet per second squared, at the surface means that objects on Mars weigh a little more than a third of their weight on Earth's surface. Mars has only 28% of Earth's surface area, but because over 2/3 of Earth is covered by water, the land areas of the two planets are comparable. Mars was an enigma to ancient astrophysicists, who were bewildered by its capricious motion across the sky, sometimes in the same direction as the Sun and other celestial objects, direct or prograde motion, sometimes in the opposite direction, retrograde motion. In 1609, the German astronomer Johannes Kepler used the superior naked eye observations of the planet by his Danish colleague Tycho Brahe to surmise its laws of motion and pave the way for the modern gravitational theory of the solar system. Kepler found that the orbit of Mars was an ellipse along which the planet moved with non-union motion. Earlier astrophysicists had based their theories on the older Ptolemaic idea of circular orbits and uniform motion hierarchies. The earliest telescopic observations of Mars in which the planet's disk was seen were those of the Italian astronomer Galileo in 1610. The Dutch scientist and mathematician Christian Huygens is credited with the first accurate drawings of surface markings. In 1659, Huygens made a drawing of Mars showing a prominent dark marking on the planet now known as Syrtis Major. The Italian-born French astronomer Gian Domenico Cassini first noted the Martian polar caps about 1666. Visual observers made many fundamental discoveries. The planet's rotation period was discovered by Huygens in 1659 and measured by Cassini in 1666 to be 24 hours 40 minutes, in error by only 3 minutes. The tenuous Martian atmosphere was first noted in the 1780s by the German-born British astronomer William Herschel, who also measured the tilt of the planet's rotation axis and first discussed the seasons of Mars. In 1877, Asaph Hall of the U.S. Naval Observatory discovered that Mars has 2 natural satellites. Telescopic studies also documented many meteorological and seasonal anomalies on Mars, such as various cloud types, the swelling and shrinking of the polar caps, and seasonal changes in the color and extent of the dark areas. The first known map of Mars was produced in 1830 by Wilhelm Beer and Johann Heinrich von Madler of Germany. The Italian astronomer Giovanni Virginio Schiaparelli prepared the first modern astronomical map of Mars in 1877, which contained the basis of the nomenclature system still in use today. The names on his map are in Latin and are planned in terms of the ancient geography of the Mediterranean area. For the first time, this map also showed hints of an interconnecting system of straight lines on the bright areas that he described as canali, Italian for channels. Schiaparelli is credited with their first description, but his fellow countryman Pietro Angelo Secchi developed the idea of canali in 1869. In the late 19th century, the American astronomer Percival Lowell established an observatory in Flagstaff, Arizona to observe Mars, and he produced ever more elaborate maps of the Martian canals until he died in 1916. To the Earth-based telescopic observer, the Martian surface outside the polar caps is characterized by red ochre-colored bright sections, on which dark markings appear superimposed. In the past, the bright areas were referred to as deserts, and most large dark areas were called maria, Latin for oceans or seas, singular mare, in the belief that expanses of water covered them. No topography can be seen from Earth-based telescopes. Changes in the surface's brightness or the atmosphere's capacity are observed. Mars' Syrtis Major side, on the last day of Martian spring in the Northern Hemisphere, photographed by the Earth-orbiting Hubble Space Telescope on March 10, 1997, among the sharpest images ever taken from Earth's vicinity. It shows the bright and dark features long familiar to telescopic observers. The North Polar Cap at the top has lost much of its annual frozen carbon dioxide layer, revealing the small permanent water ice cap and dark collars of dunes. Syrtis Major is the sizable dark marking just below and to the east of the centre. Beneath it, on the southern limb, is the giant impact basin Helias, shrouded by an oval of water ice clouds. Clouds of water ice also appear on the eastern limb above the volcanic peaks in the Elysium region. The dark markings cover about 1/3 of the Martian surface, in a band around the planet between latitudes 10 degrees and 40 degrees south. Their distribution is unusual, and their gross pattern has been observed to evolve over timescales, tens to hundreds of years. The Northern Hemisphere has only 3 major features: Acidalia planitia, Syrtis Major, and a dark collar around the pole, which were once regarded as shallow seas or vegetated regions. It is now known that many of Mars's dark areas form and adjust as winds move dark sand around the surface or sweep areas free of bright dust. Many of the luminous areas are regions of dust accretion. The canals that were figured on maps made from telescopic measurements around the turn of the 20th century are not visible in close-up spacecraft images. They were almost undoubtedly imaginary features observers assumed they saw while straining to make out objects close to the limit of resolution of their telescopes. Other features, such as the wave of darkening and the blue haze, described by early observers of the telescope, are now known to result from a combination of the viewing conditions and changes in the reflective properties of the surface. The most striking regular changes on Mars occur at the poles for telescopic observers. With the onset of fall in a particular hemisphere, clouds advance over the relevant polar region, and the cap made of frozen carbon dioxide grows. The smaller cap in the north extends to 55 degrees latitude, the larger one in the south to 50 degrees latitude. In spring, the caps recede. During summer, the northern carbon dioxide cap disappears, leaving behind a tiny water ice cap. In the south, a small residual cap comprised of carbon dioxide ice and water ice lingers over the summer. In 2 views, Mars's permanent North Polar water ice cap was gained in early northern summer 1 Martian year apart, March 1999 and January 2001, by Mars Global Surveyor. Ringing the cap, which measures about 1,100 kilometers, 680 miles across, are dark dunes marking the northern part of Vastitas Borealis. The cap's distinctive appearance reflects the spiral pattern of escarpments and valleys present in the underlying terrain. Differences in the summer frost cover can be seen by comparing the images. Though they appear small, they show significant annual changes in the heat budget for the polar cap. The arrangement of the seasonal polar caps was the subject of debate for 200 years. One early hypothesis, that the caps were made of water ice, can be traced to English astronomer William Herschel, who imagined them to be just like those on Earth. In 1898, an Irish scientist, George J. Stoney, questioned this theory and suggested that the caps comprise frozen carbon dioxide. However, evidence supporting the idea was not available until Dutch-American astronomer Gerard Kuiper's 1947 carbon dioxide detection in the atmosphere. In 1966, American scientists Robert Layton and Bruce Murray published the results of a numerical model of the thermal environment on Mars that raised considerable doubt about the water-ice hypothesis. Their calculations showed that, under Martian conditions, atmospheric carbon dioxide would freeze at the poles, and the growth and contraction of their model carbon dioxide caps mimicked the observer behavior of the actual caps. The model predicted that the seasonal caps were thin, only a few meters deep near the poles and diminishing toward the equator. Although based on simplifications of the actual conditions on Mars, their results were later substantiated by thermal and spectral measurements taken by the Twin Mariner 6 and 7 spacecraft when they flew by Mars in 1969. Early telescopic observers noted instances in which Martian surface features were obscured. They observed both white and yellow shadows, correctly interpreted as condensed gas and dust. Telescopic observers also noted periodic movements of all dark markings around southern summer. Again, they were correctly interpreted as the result of global dust storms. Spacecraft observations have confirmed that hazes, clouds, and fogs veil the surface. Extensive storm system high above Mars's North Polar region, photographed by Mars Global Surveyor on June 30, 1999. The North Polar Cap is a spiral pattern of light and dark bands at the upper left. The curl consists of water ice clouds mixed with orange-brown dust raised from the surface by high winds. The Dutch-American astronomer Gerard P. Kuiper found out from telescopic observations in 1947 that the Martian atmosphere is composed of carbon dioxide. The atmosphere is fragile, exerting less than 1% of Earth's atmospheric pressure at the surface. Surface pressures range over a factor of 15 because of the significant altitude variation in Mars's topography. Only small amounts of water are present in the atmosphere today. If at all precipitated out, it would form a layer of ice crystals only 10 micrometers, 0.0004 inches thick, which could be gathered into a solid block of ice not much grander than a medium-sized terrestrial iceberg. Despite the small amount of water present, the atmosphere is near concentration and water ice clouds are expected. Low-lying clouds and fogs are often viewed within topographic depressions, i.e. valleys or craters. Thin clouds are expected at the morning terminator, the partition line between the lit and unlit portions of the planet's disk, and orographic clouds, produced when moist air is raised over elevated terrain and cooled, form around prominent topographic features such as craters and volcanoes. In winter, westward-moving spiral-shaped storm systems are seen at mid-latitudes like Earth's. Most of these clouds, the white clouds are seen by the early observers, are composed of water ice. At least one other planetary body in the solar system besides the Earth is dissected by valleys of fluvial origin, Mars. Dust storms are common on Mars. They can occur, but are most frequent in southern spring and summer when Mars passes closest to the Sun and surface temperatures are highest. Most of the storms are regional in extent and last a few weeks. Every second or third year, however, the dust storms become global. At their peak, dust is carried so high in the atmosphere that only the summits of the loftiest volcanoes, up to 21 kilometers, 13 miles, above the planet's mean radius, are visible. Although too small to be observed from Earth, dust devils have been seen from Mars orbit and various spacecraft landing sites. Narrow tracks, assumed to be caused by dust devils, are also visible in high-resolution images taken from orbit. Dust devil in the Amazonas Planitia region of Mars, imaged by Mars Global Surveyor on April 10, 2001. The camera view is straight down, north at the top, and sunlight from the west. Visible in the scene is the faint track left by the dust devil as it moved from west to east. The light-coloured, foreshortened dust column itself, and part of the column's long shadow cast to the east. The dust devil was estimated to be a little more than a kilometre 5.6 miles in height from its total shadow length. The characteristic temperature in the lower atmosphere is about minus 100 degrees Fahrenheit, minus 70 degrees Celsius, which is colder than the average daytime surface temperature of minus 10 degrees Fahrenheit, minus 20 degrees Celsius. These values are in the same range as those experienced on Earth in Antarctica during winter. In summer, above a black surface, daytime temperatures can peak at about 62 degrees Fahrenheit, 17 degrees Celsius. Above the turbulent layer close to the surface, temperature decreases with elevation at a rate of about 2.7 degrees Fahrenheit, 1.5 degrees Celsius per kilometre of altitude. Unlike that of Earth, the atmosphere of Mars experiences significant seasonal variations in pressure as carbon dioxide, the main constituent, snows out at the winter pole and returns to a gas, sublimes, in the spring. Because the southern winter cap is more pervasive than the northern, atmospheric pressure reaches a minimum during southern winter when the southern cap is at its largest. The pressure varies by 26% as some 7.9 trillion metric tons of carbon dioxide escape and re-enters the atmosphere. This is equivalent to a thickness of at least 23 centimeters, 9 inches of solid carbon dioxide, dry ice, or several meters of carbon dioxide snow averaged over the immense area of the seasonal polar caps. Carbon dioxide makes up 95.3% of the atmosphere by weight, 9 times the quantity now in Earth's much more massive atmosphere. However, much of Earth's carbon dioxide is locked in sedimentary rocks. The Martian atmosphere is less than 1,000th of the terrestrial. The balance of the Martian atmosphere comprises molecular nitrogen, water vapor, and noble gases argon, neon, krypton, and xenon. There are also trace measures of gases that have been produced from the primary constituents by photochemical reactions high in the atmosphere. These include molecular oxygen, carbon monoxide, nitric oxide, and small amounts of ozone. The lower atmosphere supplies gas to the planet's ionosphere, where densities are low, temperatures are high, and segments are separated by diffusion according to their masses. Various constituents at the top of the atmosphere are lost to space, affecting the remaining gases' isotopic composition. For example, because hydrogen is lost over its heavier isotope, deuterium, Mars's atmosphere contains 5 times more deuterium than Earth's. Although water is only a minor constituent of the Martian atmosphere, a few molecules per 10,000 at most, it plays a vital role in atmospheric chemistry and meteorology because of low atmospheric and surface temperatures. The Martian atmosphere is saturated with water vapor, yet no liquid water is present on the surface. The temperature and pressure of the planet are so insignificant that water molecules can exist only as ice or as vapor. Little water is exchanged daily with the surface, despite the freezing nighttime surface temperatures. Seasonal water-ice ground frost on Mars, in a photograph taken by the Viking 2 lander at its high latitude 48 degrees north landing site in Utopia Planitia on March 18, 1979. Water vapor is mixed up to 10 to 15 kilometers, 6 to 9 miles altitudes, and shows solid latitudinal gradients that depend on the season. The most significant changes occur in the northern hemisphere. During summer in the north, the complete loss of the carbon dioxide cap leaves behind a water ice cap. Sublimation of water from the residual cap culminates in a strong north to south concentration gradient of water vapor in the atmosphere. In the south, where a small carbon dioxide cap remains in summer and only a small volume of water ice has been detected, a strong water vapor gradient develops in the atmosphere. The South Polar region of Mars in southern spring, in an image taken by Mars Global Surveyor on September 12, 2001. The permanent carbon dioxide cap, the bright area in the center, about 420 kilometers, 260 miles across, will remain through the coming summer, while the larger carbon dioxide frost cap, spanning most of the image, will shrink and disappear until autumn. The atmosphere water vapor is believed to be in contact with a much larger reservoir in the Martian soil. Subsurface layers of ice seem to be ubiquitous on Mars at latitudes poleward of 40 degrees. The shallow subsurface temperatures would prevent the ice from subliming. In contrast, ice is unstable at low latitudes, and any ice present in the ground would sublime into the atmosphere. The 2001 Mars Odyssey spacecraft confirmed that ice is present within a meter of the surface at latitudes higher than 60 degrees, and the Phoenix lander found ice below the surface at 68 degrees north, but it is unknown how deep the ice layer extends. Images taken by the Mars Reconnaissance Orbiter showed new impact craters at latitudes between 40 degrees north and 60 degrees north that had threatened the subsurface water ice up to a depth of 74 centimeters, 29 inches. Isotopic measurements suggest that more significant amounts of carbon dioxide, nitrogen, and argon were present in the atmosphere in the past, and that Mars may have lost much of its stockpile of volatile substances early in its history, either to space or to the ground, i.e., locked up in rocks. Mars once had a much thicker atmosphere that was lost to space through the solar wind and the sun's ultraviolet radiation, much more intense in the early solar system. Methane has also been detected in Mars's atmosphere. The Curiosity rover observed a seasonal variation in methane, but measurements from orbiters have shown only sporadic variations or even a complete absence of methane. This contradiction suggests that some process removes the methane observed near the surface before spreading through the atmosphere. Volcanoes and meteorites have been ruled out as sources of methane, which leaves chemical reactions between rock and water or metabolism by possible Martian microorganisms as potential sources. The vertical structure of the Martian atmosphere, that is, the relation of temperature and pressure to altitude, is determined by a tricky balance of several energy transport mechanisms, and by the way energy from the sun is introduced into the atmosphere and lost by radiation to space. Two factors control the vertical structure of the lower atmosphere. It is content of almost pure carbon dioxide and its content of large quantities of suspended dust. The suspended dust absorbs large quantities of sunlight and provides a distributed energy source throughout the lower atmosphere. Because carbon dioxide radiates energy at Martian temperatures, the atmosphere can respond to changes in solar radiation received. Surface temperatures depend on latitude and oscillate over a wide range from day to night. At the Viking 1 and Pathfinder landing sites, both about 20 degrees north latitude, the temperatures at human height above the surface varied from a low near minus 119 degrees Fahrenheit, minus 84 degrees Celsius just before sunrise, to a high of minus 28 degrees Fahrenheit, minus 33 degrees Celsius in the early afternoon. This temperature swing is much broader than that occurring in desert regions on Earth. The variation is most tremendous very close to the ground, and occurs because the thin, dry atmosphere favors the surface to radiate its heat during the night. During dust storms, this ability is impaired, and the temperature swing is reduced. Above altitudes of a few kilometers, the daily variation is damped out, but other oscillations appear throughout the atmosphere because of the direct input of solar energy. These temperature and pressure oscillations, frequently called tides because they are regular, periodic, and synchronized with the position of the sun, give the Martian atmosphere a very complex vertical structure. The cooling of the atmosphere with altitude at a rate of 1.5 degrees per kilometers continues upward to about 40 kilometers, 25 miles, at which level, called the tropopause, the temperature becomes a constant minus 210 degrees Fahrenheit, minus 130 degrees centigrade. This rate, measured by the Viking and later Pathfinder spacecraft as they descended through the atmosphere, was low. Scientists had expected it to be a near 5 degrees per kilometer. This rate is lower than expected for clear air because of the large suspended dust. Above 100 kilometers, 60 miles, the structure of the atmosphere is determined by the tendency of the heavier molecules to concentrate below the lighter ones. At these high altitudes, absorption of ultraviolet light from the sun disassociates and ionizes the gases and leads to complex sequences of chemical reactions. This diffusive separation process overcomes the tendency of turbulence to mix all the constituents. The top of the atmosphere has an average temperature of about 80 degrees Fahrenheit, 27 degrees centigrade. The global atmospheric circulation pattern on Mars shows many superficial similarities to Earth's, but the root causes vary. Among these differences are the atmosphere's ability to adjust to local conditions of solar heat input, the lack of oceans, which on Earth have considerable resistance to temperature changes, the great range in altitude of the surface, the solid internal heating of the atmosphere because of suspended dust, and the seasonal deposition and release of a large part of the Martian atmosphere at the poles. Near-surface winds at the Viking and Pathfinder landing sites were normal behavior and light. Average speeds were less than 2 meters per second, 4.5 miles per hour, although gusts up to 40 meters per second, 90 miles per hour, were recorded. Other observations, including streaks of windblown dust and patterns in dune fields and the many varieties of clouds, have provided additional clues about surface winds. A field of dunes on Mars's Kaiser crater floor is shown in a high-resolution image from the Mars Global Surveyor spacecraft. Wind features on several scales are apparent. The giant, relatively dark dunes, the ripples on the lighter surface across which the dunes are being blown, a different ripple pattern at dune margins and where dunes merge. The orientation of the giant dunes shows that the strongest winds on the crater floor blow from west to east, left to right. Global circulation models, which incorporate all the factors that influence the atmosphere's behavior, predict a strong dependence of winds on the Martian seasons because of the large horizontal temperature gradients associated with the edge of the polar caps in the fall and winter. Strong jet streams with east wind velocities above 100 meters per second, 225 miles per hour, form at high latitudes in winter. Circulation is less dramatic in spring and fall when light winds predominate everywhere. On Mars, unlike on Earth, there is also a north-south solid circulation that transports the atmosphere to and from the winter and summer poles. The general circulation pattern is unstable and exhibits large-scale wave motions and instabilities. A regular series of rotating high and low pressure systems were seen in the pressure and wind records at the Viking lander sites. Smaller scale motions and oscillations are ubiquitous, driven by the sun and surface topography. For example, at the Viking and Pathfinder landing sites, the winds change in direction and speed throughout the day in response to the position of the sun and the local slope of the land. Turbulence is essential in raising and maintaining the large dust found in the Martian atmosphere. Dust storms begin at preferred locations in the southern hemisphere during the southern spring and summer. Activity is at first local and vigorous, for reasons yet to be understood, and large amounts of dust are thrown high into the atmosphere. If the dust reaches a critical quantity, the storm intensifies, and high winds carry dust to all parts of the planet. The storm has obscured the entire surface in a few days, reducing visibility to less than 5% of normal. The intensification process is short-lived, as atmospheric clarity returns almost immediately, expected in a few weeks. The character of the Martian terrain has been well established from spacecraft photography and altimetry. Almost the entire planet has been photographed from orbit at a resolution of 20 meters, 66 feet, and selected areas at resolutions as high as 20 centimeters, 8 inches. In addition, the laser altimeter on Mars Global Surveyor measured surface elevations for the entire planet, averaged over a circle of 300 meters, 1,000 feet across, to a vertical accuracy of 1 meter, 3.3 feet. Many maps have been made to illustrate topography, geology, temperature, mineral distributions, and other data. After Mariner 9, the prime meridian on Mars, the equivalent of the Greenwich meridian on Earth, was defined as passing through a small crater named Airy 0, within the enormous crater Airy. Longitude was measured in degrees that increased to the west of this meridian around the planet. Later, some scientists preferred a coordinate system with longitude that increases to the east of the prime meridian. Odyssey mapped the location and concentrations of epithermal neutrons knocked off the Martian surface by incoming cosmic rays. Deep blue areas at the high latitudes mark the lowest levels of neutrons, which scientists have interpreted to show high levels of hydrogen. The hydrogen enrichment suggests large reservoirs of water ice below the surface. Despite its small size, Mars has more relief than Earth. Within the Hellas impact basin, the lowest point on the planet is 8 kilometers, 5 miles below the reference level. At the volcano Olympus Mons summit, the highest point is 21 kilometers, 13 miles above the reference level. The elevation range is thus 29 kilometers, 18 miles, compared with about 20 kilometers, 12.4 miles on Earth, i.e. from the bottom of the Mariana Trench to the top of Mount Everest. Because Mars has no oceans, a reference level for elevations had to be defined in terms other than sea level. In the early 1970s, the elevation at which the atmospheric pressure was 6.1 millibars, about 0.006 of the sea level pressure on Earth, was set at the reference. When Mars Global Surveyor gained more accurate elevation data, a better reference was needed, and the planet's mean radius of 3,389.51 kilometers, 2,106.14 miles, was chosen. One of the most striking aspects of the Martian surface is the contrast between the southern and northern hemispheres. Most of the southern hemisphere is high-standing and heavily cratered, resembling the battered highlands of the Moon. Most of the northern hemisphere is low-lying and sparsely cratered. The difference in mean elevation between the two hemispheres is 6 kilometers, 3.7 miles. The topographic boundary between the hemispheres is not parallel to the equator, but follows a great circle inclined to it by about 30 degrees. In some places, the boundary is broad and irregular. In other places, there are cliffs. Some of the most intensely eroded areas on Mars occur along the boundary. Landforms include outflow channels, areas of collapse called chaotic terrain, and an enigmatic mix of valleys and ridges known as fretted terrain. Straddling the boundary in the Western Hemisphere is the Tharsis Rise, a vast volcanic pile 4,000 kilometers, 2,500 miles across, and 8 kilometers, 5 miles above the reference level at its center. It stands 12 kilometers, 7.5 miles above the northern plains, and over 2 kilometers, 1.2 miles above the surrounding cratered southern highlands. The planet's largest volcanoes are on or near the Tharsis Rise, see below Tharsis and Elysium. Absent in either hemisphere are the landforms that result from plate tectonics on Earth. For example, long linear mountain chains similar to the Andes, oceanic trenches, or a global system of interconnected ridges. The hemispheric dichotomy most likely formed when a giant asteroid collided with Mars early in history. Gravity data, gained by Mars Global Surveyor, suggest the Martian crust is much thicker under the southern highlands than under the northern plains. The resulting northern hemisphere impact crater measures 8,500 by 10,700 kilometers, 5,300 by 6,600 miles across. The object that crashed into Mars would have been over 2,000 kilometers, 1,200 miles across. The enormous craters in the southern highlands imply an age for the surface. Planetary scientists have established from lunar samples returned by Apollo missions that the rate of significant asteroid effects on the Moon was very high after the Moon formed 4.5 billion years ago, and then declined rapidly between 13.8 billion and 3.5 billion years ago. Surfaces formed before the decline are heavily cratered. Those formed after are less so. Mars had a similar cratering history. Thus, the southern highlands almost certainly survived over 3.5 billion years ago. The southern terrain possesses several distinctive craters, huge impact basins, large filled craters with shallow, flat floors and eroded rims, smaller, fresh-looking bowl-shaped craters like those on the Moon, and rampart and pedestal craters. Hellas, the most significant impact basin on Mars, is 8 kilometers, 5 miles deep, and about 7,000 kilometers, 4,350 miles across, including the broad elevated ring surrounding the depression. Most craters measuring tens to hundreds of kilometers across are eroded, in contrast to much smaller craters formed on the younger plains, which are barely eroded. The contrast shows that erosion rates were much higher on early Mars. It is one piece of evidence that the climate on early Mars differed from what it has been for most of the planet's subsequent history. Hellas Impact Basin on Mars, shown in a topographic map bottom and an averaged elevation profile top, produced from altimetry data collected by Mars Global Surveyor through early 1999. In the map, the north is up and the south pole lies at the bottom. The black lines highlight contours of zero elevation. In both images, altitude is color-coded according to the accompanying key. Most Martian craters look different from those on the Moon. A rampart crater is designated because the ejector's lobes, the material thrown out from the crater and extending around it, are bordered with a low ridge or rampart. The ejector flowed across the ground, showing a mud-like consistency. Some scientists have conjectured that the mud formed from a mixture of impact debris and water under the surface. Around a pedestal crater, the ejected material forms a steep-sided platform or pedestal, with the crater situated inside its border. The pedestal appears to have developed when wind carved away the surface layer of the surrounding region while leaving intact that portion protected by the overlying ejector. Around 18 kilometers, 11 miles in diameter, the impact scar is an example of a rampart crater. Seen from above, its lobes of ejected material, which are bordered with a low ridge or rampart, give the appearance of an enormous mud splash. The mud is conjectured to have formed from impact debris and water under the Martian surface. High-resolution Viking images revealed an additional characteristic of the ancient southern terrain: the pervasive presence of networks of small valleys that resemble terrestrial drainage systems created by flowing water. Examples include Nergal Vallis in the southern hemisphere, north of the Argaea impact basin, and Nanedi Vallis, located just north of the equator near the east end of Vallis Marineris. Scientists have proposed two alternative mechanisms for their formation: rainfall runoff on the surface or erosion by the outflow of groundwater that seeped onto the surface. In either case, their formation may have required warm climatic conditions. A major surprise of the Mars Global Surveyor mission was an observation of small, fresh-appearing gullies on steep slopes at high latitudes. These features resemble water-worn gullies in Earth's desert regions. They were formed by the melting of ice driven from the poles and deposited at lower latitudes during periods of high obliquity. Part of the meandering canyon Nanedi Vallis on Mars, imaged by the Mars Global Surveyor spacecraft on January 8, 1998. Situated on a cratered plain near the east end of the Vallis Marineris. The channel is one of the several Martian valley networks that resemble drainage systems on Earth formed by flowing water. Some features, such as the small channel in the canyon floor, suggest that it was formed by downcutting from continual fluid flow. Other features, such as the lack of a branching pattern of smaller tributaries, suggest formation by groundwater, undercutting and collapse. The portion of Nanedi Vallis shown is about 20 kilometers, 12 miles long, and 2.5 kilometers, 1.6 miles across. Gullies on the steep north wall of a Martian impact crater on the floor of Newton crater, in a high-resolution composite image obtained by Mars Global Surveyor in early 2000. The many narrow, fresh-appearing channels appear to have been cut by fluid flow in perhaps hundreds of separate events. The rocks and soil entrained in the flows were deposited in lobes and fingers at the base of the crater wall. Some scientists have interpreted the fluid to be subsurface water that seeped from below the top of the crater wall, although other fluids such as liquid carbon dioxide also have been proposed. The smaller impact craters on the plains than the southern highlands show they formed after the decline in impact rates between 3.8 and 3.5 billion years ago. The plains can be divided into two broad areas: the volcanic plains of Tharsis, composed of lava flows, and the northern plains. The northern plains have little relief. They encompass all the terrain within 30 degrees of the poles, except for the layered terrains around it. Three broad lobes extend to lower latitudes. These include Chryse Planitia and Acidalia Planitia, centered on 30 degrees west longitude, Amazonas Planitia, 160 degrees west, and Utopia Planitia, 250 degrees west. The only significant relief in this vast area is a large ancient impact basin called the Utopia Basin, 40 degrees north, 250 degrees west. Several types of terrain have been recognized within the northern plains. In knobby terrain, many small hills are separated by smooth plains. The hills appear to be remnants of an ancient cratered surface, now almost completely buried by younger material that forms the plains. Various plains have a polygonal fracture pattern that resembles landforms found in permafrost regions on Earth. Others have a peculiar thumbprint-like texture, indicative of the former presence of stagnant ice. The origin of the low-lying northern plains remains controversial. Some scientists have proposed that they were occupied by ocean-sized bodies of water fed by extensive floods, and that the surface of the plains is composed of sediments. Parts appear to be formed of lava, like the Luna Maria. The Mars exploration rovers and spectrometers on orbiting spacecraft show that the ancient highlands are distinct from the younger plains. The rocks on the plains are typical basalts with only thin alteration rinds high in sulfur, chlorine, and other volatile elements. The rinds are formed by the interaction of the basalts with acid fogs. The rover then travelled into the older Columbia Hills, where the rocks are very different. They are basalts and impact breccias, but many are altered and rich in sulfates and hydrated minerals. Soils consisting almost entirely of sulfates or silica are also present. Due to warm surface conditions, many rocks appear to have been permeated by warm volcanic fluids or weathered. This mix of rocks and soils may be typical of the highlands. The results from orbit tell a similar story. The plains consist of primary unaltered basaltic minerals such as olivine and pyroxene. The results show surface conditions changed around 3.7 billion years ago. Before that time, warm and wet conditions were common and resulted in extensive rock alteration. After that, such conditions were rare, and rock alteration was minor. In contrast, minerals such as clays are common throughout the ancient cratered terrain. Most of the ancient cratered terrain is dissected by networks of dry valleys, 1 to 2 kilometers, 0.6 to 1.2 miles across, and up to 2,000 kilometers, 1,200 miles long. In outline, they resemble terrestrial river systems. The slow erosion of running water almost certainly forms the valleys. Many local lowlands have a valley entering and a valley leaving, showing that the lowland contained a lake. Layered deposits in lakes underlie these areas, and deltas are observed where valleys enter the lowlands. Valley networks are rare, although not absent in the younger, more sparsely cratered areas. The discovery of the valleys in the 1970s was a surprise because of the difficulty of having liquid water at the surface under present conditions. Their familiar presence in the cratered terrain shows that conditions on early Mars were much warmer and wetter than they are today. Large flood channels, termed outflow channels, are incised into the Martian surface in several areas. The channels are much larger than the valley networks, tens of kilometers across and hundreds of kilometers long. Most emerge full-sized from rubble-filled depressions and continue downslope into the northern plains or the Hellas Basin in the south. Many of the most significant drain from the south and west into Cries Planitia. These are actual channels in that they were once filled with flowing water, as opposed to most river valleys, which have never been close to complete, but contain a much smaller river channel. The peak discharges of the floods that cut the larger outflow channels are estimated to have been 100 to 1,000 times the peak discharge of the Mississippi River. Enormous events. Some floods appear to have been formed by the catastrophic release of water from lakes. Explosive eruptions of groundwater form others. The outflow channels are younger than the valley networks and mainly formed when conditions were like today. The recent discovery of very young outflow channels suggests they could form today by the eruption of groundwater from below the kilometre-thick frozen ground. 3 outflow channels near the eastern ridge of the giant impact basin Hellas, in a view obtained by Mars Global Surveyor on September 13, 2000. Stretching from upper left to lower right, they are, left to right, Deo Vallis, Niger Vallis, which joins Deo Vallis near the centre of the image, and Homachus Vallis. They are believed to be incised into the Martian surface by floodwaters moving downslope into Hellas. The channels are 1 kilometre, 0.06 miles deep, and vary along with their courses from about 40 kilometres 25 miles to about 8 kilometres 5 miles in width. Close to the equator, centred on 70 degrees west longitude, are several enormous interconnected canyons called valles marineris. Individual canyons are 200 kilometers, 125 miles across. At the center of the system, several canyons merge to form a depression 600 kilometers, 375 miles across, and as much as 9 kilometers, 5.6 miles deep, about 5 times the depth of the Grand Canyon. The entire system is over 4,000 kilometers, 2,500 miles in length, or about 20% of Mars's circumference, almost the width of the United States. Several places within the canyons are thick, sulfate-rich sedimentary sequences, suggesting that lakes occupied the canyons. Some lakes may have drained to the east to form large outflow channels that start at the canyon's eastern end. In the contrast to the Grand Canyon, which is formed by erosion, the valles marineris formed by faulting, although enlarged by erosion. Valles marineris, the most extensive canyon system on Mars, is shown in a composite of images taken by the Viking 1 and 2 orbiters. The system extends east-west for about 4,000 kilometers, 2,500 miles. Individual canyons are 200 kilometers, 125 miles across. Several canyons merge at the center to form a depression 600 kilometers, 375 miles across, and as much as 9 kilometers, 5.6 miles deep. Outcropping sedimentary rock layers in the southwestern Kandor Chasm region of Mars's Valles Marineris canyon system was photographed at high resolution by Mars Global Surveyor in March 1999. Over 100 layers or beds, each estimated to be about 10 meters, 33 feet thick, are exposed in the region, only part of which is seen in the image. Some scientists have understood these patterns as evidence that lakes once filled the canyons. The canyons of Valles Marineris end to the west near the crest of the Tharsis Rise, a vast bulge on the Martian surface over 8,000 kilometers, 5,000 miles across, and 8 kilometers, 5 miles high at its center. Near the top of the rise are 3 of the planet's largest volcanoes, Ascraeus Mons, Ariza Mons, and Pavonis Mons. Towers 18, 17, and 14 kilometers, 11.2, 10.5, and 8.7 miles, above the mean radius. Just off the rise to the northwest is the planet's tallest volcano, Olympus Mons, 700 kilometers, 400 miles across, and almost 22 kilometers, 14 miles above the surrounding plains. To the north is the largest volcano to an extent, Alba Patera. It is 2,000 kilometers, 1,250 miles across, but only 7 kilometers, 4.3 miles in height. Between these giant landforms are several smaller volcanoes and lava plains. Tharsis itself is a vast pile of volcanic rock, and although it had formed 3.7 billion years ago, it has been a center of volcanic activity ever since. The Tharsis Rise has caused stresses within and deformation of the crust. A vast system of fractures radiating from Tharsis and compressional ridges arrayed around the rise is evidence of this process. The radial faulting around Tharsis appears to have contributed to the formation of the Valles Marineris system. Olympus Mons, the highest point on Mars, in a computer-generated oblique view made by combining photos obtained by the Viking mission in the 1970s with topographic data gathered by Mars Global Surveyor a quarter-century later. The image illustrates the shield volcano's relative flatness and sloping profile. The steep, outward-facing cliff at its base, buried in places under lava that has flowed into the surrounding plains, and the complex caldera of intersecting craters at the summit. Another volcanic rise is in the northern region of Elysium, at about 215 degrees west longitude. The Elysium rise is much smaller than Tharsis, being only 2,000 kilometers across and 6 kilometers, 3.7 miles high, and is also the site of several volcanoes. A stack of layered water ice-rich sediments is at each pole, about 3 kilometers, 2 miles thick, and only a few tens of millions of years old. The layering is exposed around the periphery of the sediments, and in valleys that spiral out from the poles. The sediments are covered with carbon dioxide frost in winter, but they are exposed in summer. At the North Pole, they extend southward to 80 degrees latitude. Their extent is less clearly defined at the South Pole, but they extend farther from the pole than in the north. The layering is believed to result from variations in the proportion of dust and ice caused by changes in the tilt of the rotational axis, obliquity. Water ice is driven off the poles at high obliquities, causing the residual water ice caps to disappear and the ice to be deposited at lower latitudes. At low obliquities, the water ice caps are at their maximum. Obliquity variations also affect the incidence of dust storms and deposition of dust at the poles. The deposits have a young age because they accumulated since the last period of high obliquity when the previous sediments were removed. One peculiarity of the sediments at the North Pole is that they are surrounded by, and perhaps rest upon, a vast dune field rich in the sulfate mineral gypsum. Under present conditions, at altitudes higher than 40 degrees, ground ice is stable at depths less than 1 meter, 3 feet, below the surface, because temperatures never get above the frost point. Above 60 degrees latitude, the ice is shallow enough to have been detected from orbit. Ice was also found just below the surface by the Phoenix lander at 68 degrees north. At latitudes higher than 40 degrees, recent impact craters have excavated the surface to depths of over 2 meters, 7 feet, revealing the ground ice. There are also many surface features caused by abundant ground ice. These include polygonal fractured ground, similar to that found in terrestrial permafrost regions, and a general softening of the terrain caused by the ice-abetted flow of the near-surface materials. A striking characteristic of the 40 degrees to 60 degree latitude bands indicative of ice is debris aprons at the base of most steep slopes. Materials shed from the slopes appear to have flowed tens of kilometers away, and ground-penetrating radar shows that the aprons contain significant ice fractions. During periods of high obliquity, the ice turned from the poles concentrated on the surface at lower latitudes, forming glaciers. Modelling atmospheric circulation suggests that the preferred sites for ice accumulation during these periods are the western slopes of the Tharsis volcanoes and northeast of the Hellas Basin. These locations are rich inflow features and moraine-like landforms, suggesting that glaciers were present. The radar instrument aboard the Mars Express spacecraft detected a lake of liquid water beneath the south polar ice cap. Because the temperature of the ground beneath the polar cap is believed to be about minus 68 degrees centigrade, minus 90 degrees Fahrenheit, the water in the lake would have to be salty. The North Polar region also contains the giant dunes on Mars. The dunes, which occupy the northern part of the plain known as Vastitas Borealis, form a band that encircles the North Polar remnant cap. Interlayer of sand and seasonal carbon dioxide snow can be seen in some locations, showing that the dunes are active on at least a seasonal timescale. Seismic data collected by the InSight lander revealed that the interior of Mars has 3 layers: the crust, the mantle, and the core. The crust is between 24 and 72 kilometers, 15 and 45 miles thick. Below that is the mantle, roughly 1,500 kilometers, 930 miles thick, and more iron-rich than Earth's mantle. The iron-nickel core is molten, has a radius of 1,830 kilometers, 1,140 miles, and has a density between 5.7 and 6.3 grams per cubic centimeter, which implies that the core is over 18% sulfur. Isotopic data from meteorites determined to have come from Mars demonstrate that the planet differentiated, separated into a metal-rich core and rocky mantle, at the end of the planetary accretion period, 4.5 billion years ago. The planet has no detectable magnetic field that would show convection, heat-induced flow in the core today. Extensive regions of magnetized rock have been detected in the oldest terrains, suggesting that very early Mars had a magnetic field but disappeared as the planet cooled and the core solidified. Mars is almost undoubtedly active today, although at a superficial level. Some Martian meteorites, which are all volcanic rocks, show ages as young as a few 100 million years, and some volcanic surfaces on the planet are so sparsely cratered that they must be only tens of millions of years old. Thus Mars was volcanically active in the geologically recent past, implying that its mantle is warm and melting. Mars' gravitational field differs from Earth's. On Earth, excesses and mass deficits in the surface crust corresponding to gigantic mountains and ocean deeps, are offset by compensating masses at depth, isostatic compensation. Thus, the pull of gravity on Earth is the same on high mountains as it is over the ocean. This is also true for Mars's oldest terrains, such as the Hellas Basin and the Southern Highlands. However, the younger terrains, such as the Tharsis and Elysium domes, are only partly compensated. Associated with both regions are gravity highs, that is, places where the measured gravity is higher than elsewhere because of the enormous mass of the domes. Similar areas called mascons have been detected and mapped on Earth's moon. Because the gravity over the Southern Highlands is the same as over the low-lying northern plains, the Southern Highlands must be underlain by a thicker crust of less dense material than the mantle below it. Estimates of the thickness of the Martian crust range from only 3 kilometers, 2 miles, under the Acidus Impact Basin, which is just north of the equator and east of Syrtis Major, to over 90 kilometers, 60 miles at the south end of the Tharsis Rise. Scientists have identified over 300 meteorites that have come from Mars. Suspicions about their origin were first raised when meteorites that appeared to be volcanic rocks were found to have ages of about 1.3 billion years instead of the 4.5 billion years of all other meteorites. These rocks had to have come from a geologically active body in the recent past, and Mars was the most likely candidate. The rocks also have similar ratios of oxygen isotopes, which are different from those of Earth rocks, lunar rocks, and other meteorites. A Martian origin was proved when it was found that several of them contained trapped gases with a composition identical to that of the Martian atmosphere as measured by the Viking landers. The rocks are thought to have been ejected from the Martian surface by significant effects. They then went into solar orbit for several million years before falling on Earth. Claims in the mid-1990s of finding evidence for past microscopic life in one meteorite, called ALH 84001, have been viewed by the general science community. Little was learned about the two moons of Mars, Phobos and Deimos, after discovering in 1877, until orbiting spacecraft observed them a century later. Viking 1 flew to within 100 kilometers, 60 miles of Phobos, and Viking 2 to within 30 kilometers, 20 miles of Deimos. The Martian moons Phobos left and Deimos right were photographed by the Viking orbiters. Deimos's smooth surface is contrasted with the grooved, pitted, and cratered surface of Phobos. The central cavity on the end of Phobos is the crater Stickney. The images are not to scale. Phobos is about 75% larger than its companion. Phobos revolves around Mars once every 7 hours, 39 minutes. It moves in a close orbit at a mean distance of about 6,000 kilometers, 3,700 miles from the surface, less than twice the planet's radius. It is so near that without internal strength, it would be torn apart by gravitational forces. These forces also slow the motion of Phobos and may cause the satellite to collide with Mars in less than 100 million years. Deimos suffers the opposite fate. It moves in a more distant orbit, and tidal forces are causing it to recede from the planet. Phobos and Deimos are not visible from all locations on the planet because of their small size, proximity to Mars, and near equatorial orbits. Both moons are irregular chunks of rock, ellipsoidal. Phobos is the larger of the two. Phobos's rugged surface is covered with impact craters. The largest, the crater Stickney, is about half as wide as the satellite itself. Its surface also exhibits widespread linear fractures or grooves, many of which are geometrically related to Stickney. In contrast, the surface of Deimos appears smooth, as its many craters are almost entirely buried by acceptable debris, and it shows no fracture system. The difference in appearance between the two moons is related to the final disposition of the debris produced by effects. With the inner, more massive Phobos, the ejected material either fell back to the surface or, if it left the satellite with enough velocity to go into space, fell on Mars. For the more distant, smaller Deimos, debris was thrown off the satellite, remained in orbit until it was recaptured, sifting down to blanket its surface. A portion of the Martian moon Phobos, imaged by the Mars Global Surveyor spacecraft on August 19, 1998, The sunlit feature at the top is the crater Stickney. Many smaller craters are visible elsewhere on the satellite's surface. The grooved lines around Stickney may be fractures created by the impact that produced it. The albedo, or reflectivity, of the surfaces of both moons is very low, similar to that of the most primitive types of meteorites. One theory of the moon's origin is that they are asteroids captured when Mars formed. Since the beginning of the space age, Mars has been a focus of planetary exploration for three main reasons. It is the most Earth-like of the planets. Other than Earth, it is the planet most likely to have developed indigenous life. It will be the first extraterrestrial planet to be visited by humans. Between 1960 and 1980, the exploration of Mars was a primary aim of both the US and Soviet space programs. US spacecraft flew by Mars Mariner 4, 6 and 7, orbited the planet Mariner 9 and Viking 1 and 2, and placed LANA modules on its surface, Viking 1 and 2. 3 Soviet probes, Mars 2, 3 and 5, also investigated Mars, 2 of them reaching its surface. Mars 3 was the first spacecraft to soft land an instrumented capsule on the planet on December 2, 1971. It landed during a planet-wide dust storm and returned data for about 20 seconds. The boulder-strewn plain of Kryze Planitia on Mars. The Viking 1 lander transmitted the first color photograph of the Martian surface on July 21, 1976, one day after the spacecraft touched down. Mariner 9, the first spacecraft to orbit another planet, was placed around Mars in November 1971 and operated until October 1972. It returned a wide variety of spectroscopic, radio propagation and photographic data. Some 7,330 pictures, covering 80% of the surface, showed the history of widespread volcanism, ancient erosion by water, and the reshaping of extensive areas of the surface by internal forces. The central theme of the Viking missions was the search for extraterrestrial life. No unequivocal evidence of biological activity was found, but the various instruments on the 2 orbiters and 2 landers returned detailed information concerning Martian geology, meteorology, physics, and chemistry of the upper atmosphere. Vikings 1 and 2 were placed into orbit during June and August 1976. Lander modules descended to the surface from the orbiters after suitable sites were found. Viking 1 landed near Kryze Planitia, 22 degrees north, 48 degrees west, on July 20, 1976, and Viking 2 landed 6,500 kilometers, 4,000 miles, away in Utopia Planitia, 48 degrees north, 226 degrees west, on September 3, 1976. In 1988, Soviet scientists launched a pair of spacecrafts, Phobos 1 and 2, to orbit Mars and make slow flyby observations of its 2 satellites. Phobos 1 failed during the year-long flight, but Phobos 2 reached Mars in early 1989 and returned several days of observations of both the planet and Phobos before malfunctioning. Amid the failures of several US spacecraft missions to Mars in the 1990s, Mars Pathfinder set down in Kryze Planitia, 19 degrees north, 33 degrees west, on July 4, 1997, and deployed a robotic-wheeled rover called Sojourner on the surface. This was followed by Mars Global Surveyor, which reached Mars in September 1997 and mapped various properties of the planet from orbit for several years, beginning in March 1999. These included Mars's gravity and magnetic fields, surface topography, and surface mineralogy. The spacecraft also carried cameras for making both wide-angle and detailed images of the surface, at resolutions down to 1.5 meters, 5 feet. Close-up of the pitted volcanic rock resting on the Kryze Planitia lowland of Mars, photographed by the Mars Pathfinder lander's rover, Sojourner, on September 17, 1997. From the low perspective of Sojourner's camera, the rock appears boulder-sized, but is only about 35 centimeters, 1 foot high. Pathfinder landed on the eastern side of Kryze Planitia at the mouth of a large outflow channel about 850 kilometers, 530 miles southeast of Viking 1's landing site. Mars Odyssey entered Mars orbit in October 2001 and started mapping other properties, including the chemical composition of the surface, the distribution of near-surface ice, and the physical properties of near-surface materials. Neutron measurements suggested that the polar regions above latitude 60 degrees contain huge subsurface reservoirs of water ice. Mars Odyssey also discovered caves on a volcano by using its infrared cameras to show that the temperatures of the cave entrances, which appeared as dark circular features, did not change as much as the surrounding surface. 7 black holes on the north slope of a Martian volcano have been proposed as possible cave skylights, based on a day-night temperature pattern, suggesting that they are openings to subsurface spaces on Mars. Photographs were taken by the Mars Odyssey spacecraft September 2007. A wave of spacecraft converged on Mars in late 2003 and early 2004, with mixed outcomes. Nozomi, launched by Japan in 1998 on a leisurely trajectory, was the first to reach the planet's vicinity, but malfunctions prevented it from being put into Mars orbit. In mid-2003, the European Space Agency's Mars Express was launched on a half-year journey to the Red Planet, carrying instruments to study the atmosphere, surface, and subsurface. It entered Mars orbit on December 25. However, its British lander Beagle 2, which was to examine the rocks and soil for signs of past or present life, failed to establish radio contact after having landed on the Martian surface the same day. Within weeks of its arrival, the Mars Express orbiter detected vast fields of water ice and carbon dioxide ice at the South Pole, and confirmed that the southern summer remnant cap contained frozen water like the northern one. It also detected large sulfur-rich deposits in Valles Mineris and clay minerals in the cratered terrains. Also launched in mid-2003 was the US Mars Exploration Rover mission, which comprised twin robotic landers, Spirit and Opportunity. Spirit touched down in Gusev crater 15 degrees south, 175 degrees east on January 3, 2004. 3 weeks later, on January 24, Opportunity landed in Meridiani Planum 2 degrees south, 6 degrees west, on the opposite side of the planet. The 6-wheeled rovers, each equipped with cameras and a suite of instruments that included a microscopic imager and a rock grinding tool, analyzed the rocks, soil, and dust around their landing sites, which had been chosen because they appeared to have been affected by water in Mars's past. Both rovers found evidence of past water. Perhaps the most dramatic was the discovery by Opportunity of rocks that appeared to have been laid down at the shoreline of an ancient body of salty water. Each rover was designed for a nominal 90-day mission, but functioned well past that time. Spirit and Opportunity stopped transmitting to Earth in March 2010 and June 2018. Opportunity had covered 45 kilometers, 28 miles over 14 years, which were records for distance driven and mission time spent on another planet. A portion of rock outcropping within a small crater in the Meridiani Planum region of Mars, shown in an image made by the Mars Exploration Rover Opportunity in late January 2004. The outcropping varies in height from 30 to 45 centimeters, 12 to 18 inches, along the crater. As interpreted by rover mission scientists, the rock layers were laid down as deposits at the bottom of a body of flowing saltwater on the shoreline of an ancient salty sea. In 2005, the US launched the Mars Reconnaissance Orbiter, carrying an imaging system with a resolution of 20 centimeters, 8 inches, a spectrometer to determine the surface composition, and a ground-penetrating radar. The imaging system took photographs of dark streaks that appeared to be salty water flowing downhill after melting during the Martian spring. The spectrometer revealed that clay minerals and other alteration products indicative of a warm distant past are common in the ancient cratered terrains, while the radar determined the thickness of the ice at the poles and detected glaciers elsewhere. In 2008, the US probe Phoenix landed in the north polar region of Mars. Phoenix carried a small chemical laboratory to study the Arctic soil, It found water ice underneath the surface of Mars and alkaline soil. The US Mars Science Laboratory rover Curiosity landed in Gale crater in 2012, weighing about 900 kilograms, 2,000 pounds, and measuring about 3 meters, 10 feet long. It was the heaviest and longest rover on Mars. Aeolus Mons, also called Mount Sharp, the crater's central mountain, comprises many layers of sedimentary rock laid down over much of Mars's geological history. Gale crater is at a low elevation, so it would have been pulled there if Mars had ever had surface water. Curiosity took pictures of water-transported gravel, which suggests that Gale crater was likely the floor of an ancient stream at one time. Curiosity also found that early Mars could have supported life. It discovered traces of organic molecules preserved in rock layers 3.5 billion years old, and that the amount of methane in the Martian atmosphere varies with the seasons. In September 2014, 2 probes entered Martian orbit. The US Mars Atmosphere and Volatile Evolution MAVEN probe studied the upper atmosphere and found that Mars had lost most of its early atmosphere to the Sun's ultraviolet radiation and solar wind. India's Mars Orbiter mission MOM probe was that country's first to reach another planet. Its instruments included a color camera, an ultraviolet spectrometer, and a sensor for methane. The ExoMars mission was a joint European Space Agency and Russia project. The first part of the mission arrived at Mars in October 2016 and comprised the Trace Gas Orbiter TGO and the Schiaparelli lander. Schiaparelli ejected its parachute early and crashed into the surface. The TGO mapped the vertical distribution of dust and water vapor in the atmosphere. It did not detect any methane, which conflicted with Curiosity's detection and suggests that some process destroys methane before it spreads throughout the atmosphere. The US InSight, Interior Exploration Using Seismic Investigations, Geodesy and Heat Transport, lander touched down on Elysium Planitia in November 2018. InSight placed a seismometer on the surface that made the first detections of quakes on Mars and revealed the planet's internal structure. The lander also deployed a probe that burrowed into the ground to study heat flow in the soil. However, the probe seemed to have hit some underground obstacle, such as a rock or gravel, because it stopped before reaching the desired depth. The same rocket that launched InSight also carried 2 CubeSats, small satellites whose basic unit is a modular cube measuring 10 centimeters, 4 inches square per side. Each InSight CubeSats, called Mars Cube 1 Marco, comprised 6 such units. The first CubeSats to be launched to another planet, they relayed communications to Earth from InSight during its landing. In February 2021, 3 missions arrived at Mars. The United Arab Emirates orbiter, HOPE, carried a camera and infrared and ultraviolet spectrometers to study the Martian atmosphere. The Chinese mission Tianwen-1 comprised an orbiter and a small rover, Zhurong, which landed on Mars on May 14. The American Mars 2020 mission carried the Perseverance rover, which had a drill designed to collect core samples that could be taken to Earth for analysis. Perseverance landed on February 18 in Jezero crater near a dried-up river delta and searched for signs of ancient microbial life. The rover also carried a small helicopter, Ingenuity, which on April 19, 2021 became the first machine to fly through the skies of another planet when it ascended to a height of 3 meters, 10 feet. Shadow of the Ingenuity helicopter on the surface of Mars. Image was taken during the first flight of a machine on another planet. April 19, 2021. Ingenuity used its navigation camera, which tracks the ground during flight, to take pictures. Future missions scheduled to arrive at Mars include the second part of the ExoMars mission, the Rosalind Franklin rover. Rosalind Franklin will arrive in 2023 and carry a drill that can reach 2 meters, 6 feet underground to collect soil samples for onboard analysis. From the beginnings of telescopic observations of Mars, people have speculated whether life could have started on the planet and what that life might be like. Early observers were concerned with intelligent life, but now the focus is on life's origin, microbial communities, and limits to their survival. Views on the prospects of life for Mars have varied in recent decades. In the 1960s, the possibility that changes seen at the telescope could have a biological cause led to Mariner 9's attempts to monitor surface changes in 1972, and the launching of the Viking landers to Mars in 1975. The Viking spacecraft had an array of sophisticated experiments to detect metabolism and organic molecules. The negative results from these experiments resulted in a considerable pessimism that continued through the 1980s to the prospects for life. However, several factors subsequently contributed to a more optimistic view. Recognition that life can survive in a far more comprehensive range of conditions than thought, including near deep sea vents at temperatures well over 1,000 degrees centigrade, 1,800 degrees Fahrenheit, in basaltic rocks deep below the surface, very saline and acid environments. The discovery that life started on Earth before the heavy bombardment shows that life's origin is not an extremely low probability event, but will follow if the right conditions are present. Mounting evidence that conditions on early Mars were Earth-like when life arose on Earth, a fourth factor is a recognition that Earth and Mars exchange materials. As stated above, over 30 pieces of Mars have been found on Earth, despite the difficulty of distinguishing Mars rocks from Earth rocks. It is more challenging to get Earth rocks to Mars. During the heavy bombardment, when life may have already started on Earth and conditions on Mars were Earth-like, pieces of Earth may have been transported to Mars. Thus, life may have originated independently on Mars or been seeded from Earth. In 1996, the scientific world was shocked when scientists announced they had found evidence of life in a Martian meteorite. To support their conclusion, they listed bacteria-like objects in electron microscope imagery, detection of hydrocarbons, mineral assemblages that were not produced in chemical equilibrium, and magnetic particles are like those produced by some terrestrial bacteria. The announcement triggered a vigorous scientific debate into the validity of the claims. The scientific consensus now is that there are plausible biological explanations for all the observations and that the claims are likely invalid. Despite this setback, the key driver of the Mars exploration program is still the search for life. Because liquid water is so essential for life, the initial focus has been on searching for evidence of warm conditions that would enable the persistence of liquid water. The evidence for such conditions, at least on early Mars, is now enjoyable, and there is some evidence that liquid water sometimes flows on the surface in a few places. The exploration will search for more direct evidence, such as organic remains and isotopic signatures. The Martian meteorite debate and disagreements about early terrestrial life point to the difficulty of finding compelling evidence of microbial fossil life. Perhaps the best strategy is to look for fossil remains from the early period in Mars's history, when conditions were more Earth-like. Perhaps the best strategy is to look for present-day life in niches, such as warm volcanic regions, or the intermittent flows of what may be briny water, hoping life would survive where conditions were hospitable if it ever started on Mars. Human exploration is still decades away, despite optimism when the Apollo program ended in the early 1970s that Mars exploration would soon follow. The technical difficulties of getting people to Mars and back, while challenging, are not overwhelming. The significant difficulty has been in a compelling rationale to justify the tremendous costs and risks. Advocates have argued that exploring Mars and extending human reach beyond Earth-Moon space needs no practical rationale. To explore is an essential part of being human. Others have argued that practical benefits, such as economic stimulus, scientific discovery, and technology feedback would result. Despite many powerful advocates, human exploration of Mars now seems far from reality than in the 1970s. Several studies have been undertaken to determine how human missions to Mars might be implemented. There are two basic classes of missions that follow the orbital motions of Mars and Earth. The round-trip time is 500 to 600 days in opposition-class missions, with 30 days on Mars. For conjunction-class missions, the round-trip time is about 900 days, and the time spent on Mars may be as much as 550 days. Most studies conclude that the short stay time for opposition-class missions could not justify the cost and effort of getting there, and that despite the more excellent resources needed, a conjunction-class mission is preferred. There are many variants of how such a mission might be implemented. In some scenarios, a cargo ship is sent ahead of the humans to establish an operating base, and the humans follow years later. In other variants, all the resources needed to accompany the crew. Another issue is the extent to which Mars resources could support people during their stay and make oxidants and propellants for the return trip. In situ resource units, ISRUs, could be sent to Mars well ahead of the people to extract and store both oxygen from the atmosphere and hydrogen from water, using solar or nuclear power. People would not be launched from Earth until adequate resources for mission success had accumulated at Mars. The atmosphere at Mars and Earth could decelerate, aerobrake, the outgoing and incoming spacecraft to save fuel. An additional option is a direct entry. Another issue is what the astronauts would do at Mars. Should they stay close to a base and operate remote robots at various locations around the planet? Or should they go on extended trips from the base and explore, incurring the risk of being stranded? One issue that is not susceptible to quantitative engineering analysis is crew health. Long times in space have various physiological effects. The circulatory and vestibular systems are affected, and bones tend to demineralize. The crew would also experience psychological pressures from several hundred days in a confined space far from Earth, with no other company. Radiation effects would also be significant if solar storms occurred during the 2 to 3 year trip. Countermeasures to minimize degradation in human performance would have to be devised. Planetary protection is another issue. The first concern is scientific. Mars should not be contaminated with terrestrial materials before the potential for indigenous life has been assessed. Robotic spacecraft sent to Mars are subject to rigorous cleanliness requirements, and parts that touch the surface are sterilized to minimize the possibility of interfering with the detection of indigenous life. Similar protective measures cannot be followed for human missions. The second issue concerns back contamination. International protocols require that materials returned from Mars be quarantined until proven safe. The astronauts may have to be quarantined. Most of the planetary protection issues should be resolvable well ahead of human missions by the robotic return of Martian samples.
Jai Mamari Nina. Jordan Laraba. Kafana Lana Tula. Jai Mamari Nina. င်းလာ